Okie dokie. 17.7 and 17.8 are both going to start with recall Green's theorem. And the reason why it's going to happen that way is because there's two forms of Green's theorem, because there's the side that we're talking about circulation, and there's the side where we're talking about flux. We're going to start with the circulation side. And so we're recalling Green's theorem. Green's theorem for circulation. And that's going to be the closed line integral for some sort of a curve in space. F dot dr is, again, your contributions of curl, your rotation around the boundary, being the same thing as the total cumulative amount of rotation, that is the curl gx minus fy, in the region that you closed. So here is the circulation along the boundary, C circulation. A net amount of circulation that's accumulated as you go around the boundary is the same thing as just taking a look at summing up all of the rotation that's happening inside of the boundary you closed. The boundary, what's on the outside, reflects the sum total of what's on the inside. And that's just the general principle that's going to be what the rest of the fundamental theorems of calculus are. So I'm going to draw, I made this little chart because this will help you connect the dots from what we've spent a lot of time focusing on between Green's theorem and this new idea, Stokes theorem, because it's really just an extension. And I want you to see it as just an extension. So Stokes theorem. So all the important players are going to be just repurposed and kind of redescribed into the three-dimensional case for Stokes theorem. So the first thing that we need to repurpose is essentially what our region R is that we're talking about. So the region in Green's theorem, which we're in 2 dimensions, so R is a subset of R2. So we have some 2-dimensional R, which we call a region, some region, and that's going to get changed now into being a surface. So instead of just being a 2-dimensional region, now we have a 3-dimensional surface S, which will be S is a subset of R3. It's a surface. Okay, and then again, the relationship between R and that is, and so the C is the thing that's bounding it. So C in Green's theorem, which was the boundary of R, so boundary of R, that's going to now just be the boundary of the surface. And we still call it C. So C is now the boundary of the surface S. Now, again, the main extension is Green's theorem, we're stuck in the plane. That's a 2-dimensional idea. Stokes, now we can be in 3 dimensions. We can have 3-dimensional space. And so what I'll do is I'll represent it like this. Before, in Green's theorem, the curl, and curl is cross product. Do you guys still remember that one? And then because that we reserve the dot product for which one? Divergence, right? So curl, cross product, divergence, dot product. It's very nice that those happen to have the same starting sound. So this is a vector because curl is a cross product. Cross product is not a scalar quantity, that is a vector. So we need to say that this vector has 2 components. In other words, it's in 2 dimensions. That's Green's theorem. So the curl, the difference we're going to change is going to be what? You tell me. Yeah, so the curl, del cross F is in what? Good, R3. All right. And so when we're actually looking at the Green's theorem is a special case of Stokes theorem, actually. And it's going to be this idea of we're taking a double integral R, the curl. So I'm rewriting this. So instead of putting gx minus fy, I'm going to just put the curl. And what's really going on is we're taking that dot product. If you go back, it's in the notes. That's why I included that full picture when I showed that the relationship between K being that the component up there, dA. So K is acting like a uniform normal. In other words, we're always stuck flat in the plane and K is sticking up. And so instead of restricting this to being in the plane with the normal of being only K, now we're just going to have any unit normal vector that's going to be allowed. So we're going to have over the surface, so double integral over our surface, we have now 3-dimensional curl. That's going to be allowed over an arbitrary oriented unit normal n over the surface. So it's the surface integral. Okay. And then I'm gonna put one more picture up here, and then this entire board is going to be like a good thing. So here's Green's theorem. Actually, let me do dotted lines. That's not. So Green's theorem is going to have a two-dimensional region. So if I took like here's x, here's y, and this kind of a diagram should be very familiar to you by now, right? We have C and R, where C is closed because we start and stop at the same place, and we enclose this region R in the plane. This is what Green's theorem is relating to. And then now we're extending this to 3 dimensions. And so my art skills aren't peak, but I practiced these last night so that I could draw it. And this is existing in 3-dimensional space. So it's like, okay. And then this boundary at the bottom here that goes around, this is the curve C. And the actual surface S is kind of like the actual. So let me think about, I basically drew a parachute. So 3-dimensionally, I'm trying to represent like a parachute. So this isn't a solid. So this isn't a solid. This isn't like a snow globe. This would be like if you took a parachute stuff and now it's flying, and so you like made it poof up kind of thing. So that is what we're calling S. S is the cloth that essentially poofed up the surface. So what we're saying is in Green's theorem, the total amount of rotation that's happening restricted in the plane inside is the same as just the net amount of rotation that's happening along the boundary. The same thing is going to be true here. Now, Stokes is a little bit more general and it's more powerful because it's saying now technically that surface doesn't need to be stuck inside of the plane. So long as it's bounded, so long as we know where the boundary, say, of like your thing is. So it's like if you had a parachute, the very, very edge of the parachute is kind of like the boundary. No matter how you kind of orient the rest of the surface, the total cumulative amount of rotation that's happening on the surface will be just the same thing as if you look again at the boundary. So the boundary is always going to give a reflection of the net accumulated effect of all the stuff that's happening inside of the actual surface, on the surface, whether that's curl or divergence. Okay, so this is the board that you want to get the picture of. Okay, this is the summary for Green's to Stokes theorem. And then we'll actually talk about, I'll write down what the theorem is from the book. But this is going to help, this is the far more useful board, I would say, in terms of relating all the concepts. So everyone got this one for sure. Picture of it or something. Okay, going once. Twice. Yep. So here's now the statement of the theorem. So now that you have the setup for what the theorem is actually saying, now with that in mind, try to interpret all the stuff and the conditions of the theorem. Make the conditions of the theorem adhere to your now visual understanding of what this is really saying. Going backwards in that sense with retrospect is a slightly easier way to do this. So we're going to let S be an oriented surface, be an oriented surface in R3, so like a 3-dimensional surface with a piecewise smooth, closed boundary, and we still call that C, whose orientation is consistent then with that of S. S. And then we also want to assume that we have a field in 3 dimensions, so we need 3 components. We'll call that F, G, and H. This is a vector field whose components have continuous first partial derivative, we just need that to compute the curl basically on S. And then here's now the equation that we essentially constructed already, is that this closed line integral F dot dr, so it looks very similar to Green's theorem, again, we're just extending it, is now a surface integral, so a double integral over the surface S, summing up all the total amount of rotation contributions, all of the curl, summing up all of the curl with its relationship to the oriented surface across the entire surface. That, again, total amounts of rotational contributions on the inside of the surface can be found equivalently by seeing the net amount of rotation on the boundary. That's the gist of this. And then we'll just specify where n is the unit vector. The unit vector normal to S, to X, determined by the orientation of S. Okay. So, and I have started here basically the accumulated rotation of the vector field over your surface S is going to equal the net amount of circulation. Same idea over and over again. So it sounds like I'm repeating myself from when I was teaching Green's theorem. The reason is because I am intentionally repeating myself. It's the same. It's just now we've built tools to actually talk about this in 3 dimensions instead of being stuck in the plane. Because being stuck in the plane isn't all that useful when plane and aerodynamics and rocks and ships and everything exists in 3 dimensions. So there's a statement of the theorem, but you already had this, okay, from the construction and the comparison to Green's theorem. So I want to show you something, just to kind of reiterate that this kind of equation. And we were talking about conservative fields, and essentially, if you have a conservative field, there's no amount of rotation going on. So if you have no rotation, that is no curl, then that is actually going to point back and say, okay, then your field is conservative. We can show that now using this. Actually, no, yeah, I'll let me erase this. You got this in your notes because you want to reference this in the next thing. Cool. This isn't something that I'm not necessarily going to test you on, but it's pretty enough to be taken out of the textbook and actually talked about. So if we have the curl of a field, and something a habit that I'm trying to instill in you when I do this, the reason why I'll never use PowerPoint slides is because the hardest part for me when I was learning math, especially with new symbols in it, was what English am I even saying to correspond with the idea, right? So when I write out this del cross F and I say the curl, and then that's emphatic. And there's a reason for that, because then when you're practicing on your own, you don't have to go, okay, upside down triangle with the cross sign, vector field. That's curl. Because the more you don't associate what the idea is in the relationship with its notation, the harder it'll be to kind of assimilate in your own personal practice. So the curl, if the curl is equal to 0, now before I finish this, tell me, is this a scalar 0 or 0 vector? Yeah, it's vector. Why is it vector?
Because we have a cross
product. Yeah, cross product spit out vectors. Now, if I had done divergence equals 0, if I had done a divergence being 0, then that'd have been dot product, okay? But this is the curl being 0. And if we can show that the curl is 0, we're proving this direction, essentially. We're proving that this will mean that, okay, again, I'm gonna write notation and say the English of what the concept is. F is a conservative field, okay? You see what I did there? So by saying F is conservative, what comes along with that for free is this idea that by definition, that means it's going to be the result of taking the gradient of that potential function. And so instead of just seeing curl or del cross F equals 0 vector implies field is gradient of potential, you could read it like that. But what's really happening is I'm trying to show you curl being the 0 vector is going to result in there being a conservative field. No rotation, okay, you got a conservative field. So relate the words to the symbols. And then now you'll realize that those really, really thin, dense math books in the library, which will have like one paragraph of something like that, that's containing about a chapter's worth of undergrad mathematics to understand. Okay, so it's a very, very dense language that we use a lot. So trying to get you exposed to some of that before you're out of my care. So here's the proof for it. It's going to be very simple, very straightforward, because the only reason it's straightforward is because we've developed Stokes theorem. Okay, so using Stokes theorem is a really, really powerful theorem. We can start with the line in F dot dr. So this amount of circulation. And let's cite Stokes. So by Stokes, we know that this is going to be equal to what? And you can use your notes. Yeah, surface integral curl. That's the main thing I want you to know there. Not the divergence. If we're talking about circulation, this is the integral of what? Curl. Curl. And then dot and S, capital S, because we're talking about the surface differential now. It's like the little patches that you sew together into a quilt. And then now, the condition of the theorem is that we have no curl. Curl is 0 vector, okay? And so we can plug that into Stokes theorem. So S, we have 0 vector dot n es. Okay, well, 0, 0, 0, 0, 0. This is going to be equal to 0. And the gradient, so to be conservative, we're basically saying that the line integral over a closed path is going to be equal to 0. It's going to be path independent. It doesn't matter what path you take. If you're closed and you're conservative, we talked about that. Which section did we talk about that? I think we talked about that in conservative fields. That's like 4 sections ago. Yeah. So what's implicitly stated here is we got to recall that a conservative field, if I have a conservative field, that's true if and only if the line integral f dot dr that's closed is equal to 0. So that's kind of the implication here. Cool. Okay, so let me know when you got that, and then we're gonna do a pretty long computation. Question?
When we were doing surface integrals, does the normal vector have to be a unit normal or just the?
In the definition for the surface integrals, this n is given by being a unit, or having magnitude of 1. Because well, if it wasn't, then we would be changing the value of the curl. Essentially, we'd be scaling it. So we're trying not to change. We're essentially multiplying by 1 using a vector. Yeah. So n can't just be any normal vector. It's got to be unit. Okay. We got this? Example. Is going to be, let's consider for a second we have the field Z minus z and x squared minus y squared. And then we want C to be a curve where C consists of the 3 line segments on that bound. Then we'll have Z equal to, what do we use here? 8 minus 4x minus 2y in the first octant. Oriented, we need to orient the surface. So oriented from, so it'll start at 2, 0, 0, and from there go to 0, 4, 0. From there go to 0, 0, 8, and then from there it'll cycle all the way back around to the first point, 2, 0, 0. And then we want to use Stokes theorem to evaluate the closed line integral f dot u. Now, if you didn't use Stokes theorem, here's what you'd have to do. You'd have to take and parameterize 2, 0, 0 to 0, 4, 0. That would be C1. Then you'd have to go parameterize 0, 4, 0 to 0, 0, 8, C2. Then you'd have to parameterize 0, 0, 8 back to 2, 0, 0, C3. Then what you would do is you would say that the overall closed CF dot dr is the line integral not closed C1 f dot dr, line plus the line integral C1 to f dot dr plus the line integral C3. And then for each one of those integrals, you'd have to take the r that is given from whatever line that you had to do, find 3 separate drs, take 3 separate dot products with the field, substitute all the different x and y values in, get everything in terms of your t's that you parameterize your line segments to, and then smash all 3 of those together, and then you get your final answer. So is it possible? Yeah. Is that horrible? Yeah. So that used to be a lab question. It is no longer, I don't think. No. We'll find out. Yeah. Yes, it was. That was not fun. That really was not fun. We had to do this both ways in the same method. Yeah. Okay, but that's why Stokes theorem is here. Because Stokes theorem is going to give us a way to relate the f dot, the closed f dot dr to simply a surface of basically. But we need a picture, otherwise it's kind of difficult to visualize what's going on from just this. So let me try to do some art. This is such a bad idea. Okay, actually, let me do this. I'm gonna need more space on the board. You guys have this? Yep. Written down? If you have this written down, then I can just rewrite the diagram. Okay. So, do you recognize what kind of a surface the z equals the 8 minus 4x minus 2y is? Well, paraboloid is going to, paraboloid sounds like parabola, and parabolas have quadratic terms in them. And we don't have a quadratic term in this, but we do have this linear terms. And so what's the 3-dimensional kind of extension from when we did linear lines? We have planes now. So this is just a plane. And because the coefficients are both negative for the x and the y, this isn't growing plane, this is a decreasing plane. So it's kind of like a roof that's like slanted down into the quadrant. So let me do this. Here's going to be the origin, and it will be that, and then here's our point of interest. So here's the x-axis, and then we're gonna have solid y point of interest, and then we're gonna have z, and this will be a point of interest. So this point right here is the one that's the 2, 0, 0. So that one is 2, 0, 0. And then we're taking 2, 0, 0 over to 0, 4, 0. This is 0, 4, 0, and so straight line. Bingo. That's part of C. 0, 2, 0, 0, 0, 4, 0. And then we go from 0, 4, 0, and we want to go to 0, 0, 8. This up here is 0, 0, 8. Oh, okay, that's a little trickier. All right, this way. And then point it like that. The C is continuing around. And then we're going from 0, 0, 8 down to 2, 0, 0. So that's gonna be. Dang it! We were doing so good. Let me try that. If I could describe to you how much time I wasted last night practicing drawing these. Okay. It's close enough. You guys can see what's going on, right?
Yeah.
So it's the curve, the boundary of this is the C that's going around because we're bounding the plane into the first one. That's the chunk that we're interested in. Okay, and then R is this region down here. I want you to see this as being in the XY plane that's shaded. See that? The area underneath this plane that's been snapped down. So what we have is that S, the surface that we're talking about, that's given explicitly by the Z is equal to 8 minus 4x minus 2y. So that is just the overall surface, right?
Is the R similar to when we did the when we were doing vectors, so it was the unit or the vector that came down. The vector went up and then the shadow of the vector down.
Projection.
Kind of, I think of the R as being like, so if you were building like a fort and the sun is beaming down at noon, and then you slant down a piece of like cardboard or something like that, that's the shadow it produces underneath if you were to pitch that up against a tree or something. Because this region of integration is what we're going to be interested in here. The actual to orient yourself in the three-dimensional like kind of depiction here on the whiteboard is that the normal vector sticking off the surface is kind of like that. So that would be like your end. It's normal to the surface. Okay. What is this R being described by? Well, this R, the description of R, we'll need this. It's points x, y. And so the x is going between basically x is 0 up to x is 2. 0 less than equal to x is less than equal to 2. And as for the y, though, well, we start at 0, right? Because this is y equals 0 down here. And then the relationship between that, this is the upper bound, this line equation that's basically formed. Right? Now, look at what value of z are we when we're in the xy plane? 0. Okay, so if we just take for a moment and take this and say 0 is equal to 8 minus 4x minus 2y, then if I take this over, I got 2y is equal to 8 minus 4x, or just y is equal to 4 minus 2x. Everybody good with that? That's how we know what the upper bound here is. It's 4 minus 2x. That's this component in the x-y. All right. You'll see why we'll need that in a second, because when we convert this over from the surface integral, we'll need these bounds. So make sure you have these in your notes, so that because I'm going to refer to these in a little bit once we've computed some of this stuff. Okay. I will always put a little cross through my Z's for the reason that I know my handwriting is not that great. Yeah. Going once. Going twice. So. While I'm erasing this, flip back in your notes to when you wrote down Stokes theorem so that you can see what the line integral is actually related to. And you'll notice that the line integral is related to a surface integral where we're summing up the curl. So as the means a reminder here, Stokes theorem is basically going to have that the thing that we're desiring to compute. Because again, don't lose sight. This is the thing that we're trying to find. So the entire question is about this right here. And Stokes theorem is going to let us relate it to the surface integral S, the curl dot n ds. So we got to answer a few questions here. What is this? How are we going to represent this? And then also, how are we going to get this out of the surface integral bounds to a rectangular bounds? And so we've already answered the rectangular bounds thing with R by drawing the picture. But now we can actually compute what this is. So the curl is going to be curl of n, which is the curl. So in this case, how many dimensions do we have?
3.
So what is del operation?
Partial x, partial y, partial y.
And so we have all three components for the partials. And then we're taking the cross product with the field. Now the field was given in as part of the question, so you don't have to derive this. It's just z minus z and then x squared minus y squared. Okay. So when you set this up, you get that 3 by 3 determinant, right? You get the I, J, K, and then the first quote vector, the partial x, partial y, partial z. And then what are we putting on the bottom right here?
Z x squared.
Okay. Wellness check. Everyone good with setting this part up? We're trying to find the curl. We're trying to identify this guy. And in so doing, we set it up. Definition of what the del operation is. Here's the field that we actually had. Just a matter of plugging in those components in their appropriate locations. So everyone feels solid on that. They can put that together. Okay. So now it's just a matter of doing the computation. I'm going to be more tedious here than you'll need to be. But just for the sake of, we technically haven't done a full curl thing in the lecture, so it'll be good to go through it. When we do the i's, it's going to be pretend like this 2 by 2 is the new determinant here. So we've got partial y with partial z minus z and x squared minus y squared. And then do we add or subtract the next piece?
Subtract.
Good. Don't forget that because that will cost you. And then J is now we're taking the x and z, so partial x, partial z. Then we get z here, and then x squared minus y squared. That's going to go with the J component. And then what do we do? What's the last piece here?
Plus.
And then with K's, right? So K, this is now gone, so we're taking this 2 by 2. And then partial x, partial y, z and minus. Okay, so let's actually see what these 2 by 2 determinants would give. And so I'm going to use the hard bracket because we'll be using parentheses, so it's more clear what's outside and what's inside. Again, so we go across like this. So y, the partial y is associated diagonally to the x squared minus y squared. So it'll be partial y, x squared minus y squared, and then minus this diagonal. So z with this. So it'll be partial z minus z that. Okay, so that's with I. Is everybody good with this one? Because if you're good with this one, it's pretty much all the same. You just repeat the pattern over and over. Okay, and then now minus. This is gonna get some people, I just know it, so be careful. Minus, and then partial x. X squared minus y squared, because that's diagonal, so it's just diagonal, subtract this diagonal. Minus partial z of z. And that's good. Okay, and then we add last bit. So in this 2 by 2, we get partial x with minus z. And then we're subtracting this diagonal, partial y with z. And that's the k component. Okay, another wellness check. So if we got, who's good setting the very first line up here? And then breaking it down into what the 2 by 2s individually are going to be. Is that good? And you see how this is just, tedious with showing where every single part of the derivative comes from. You don't have to show this stuff, okay? So if you're in your head, you can just be like, well, that's going to be minus 2y. That's better than showing all this. But this is going to be just for the sake that it's there. Yes.
Do you want us to show all the 2 by 3? Or can we just go from 3 by 3 to
I would show this one just for the reason that this still lets you have the possibility of making a silly arithmetic mistake on forgetting which order to subtract, because it's this. This is the main thing that is annoying. So if once you get to here and you really solidify that you know which way the sign is going to flip, then it's fine. But unless you've done like 1,000 of these and can just in your head, which is so do what you know you can do with 100% accuracy. Let's do that. So if you know you can do that with 100% accuracy without needing the intermediate stuff, by all means, that's the whole point of doing that. But if you need to show this stuff, if you're either A, dyslexic like me, or just are paranoid, also like me, then you can show this. Okay, so now we can actually just take out derivatives, right? So this component for I, we're gonna have that's going to be minus 2y. That's going to be, notice that this is going to be minus 1, and then we're subtracting minus 1. So it looks like just plus 1 at the end. I'm going to keep the minus sign out here. I'm not going to flip it around yet, just because. You don't want to try to combine in steps with out steps, because then your brain says, wait, did I already account for it? And then you don't need that second dot. Okay. Now with respect to x, what's that?
2x.
Okay, so just a 2x. And then minus 1. Notice that I don't need to double count or worry about my signs, because I'm simply going to save that step for later. So I strongly recommend doing that. As in, how about just do it that way? Because if you practice it the right way, you'll be fine. Plus, well, that's convenient, right? Because 0 and 0, so we just go 0, 4. Okay. So if I write this as a vector, because ultimately curl is going to spit out what?
A vector.
Then the components of this vector, what's the x component of the vector?
Negative 2y plus 1.
Yeah, for style points, I just go 1 minus 2y. And then, yeah, so then 1 minus 2x, that's kind of cool. Now that's where you can apply that minus sign, flipping it around. And then 0 is 0. Or should I say 3? Okay.
Yes.
And just write a 3 in there.
0 now equals 3.
Okay.
3 is closer to 0 than it's a 10, so
All right, wellness check. Everyone, so can you get the curl?
that's wrong. Yeah. You probably possibly is one because
Okay. Going once. All right, so save this in your notes. You'll need this because we'll be plugging it in. Well, after we find with normal, but yeah. We'll be plugging it in. So let's recall, so the normal is with respect to what the surface. So z is equal to 8 minus 4x minus 2y. This is what the surface was. Now we need to get the normal. And so if you remember from chapter 14, I want to say, when we did the normals for surfaces, the normal of a plane given explicitly is the vector minus zx minus zy and 1. So we went through that back in, I believe, chapter 14. So you don't need to reprove that, just memorize that you knew it once and then use it. Because this is going to make finding the normal vector super easy. You might ask yourself, why on earth do we care about the normal? Well, Stokes' theorem says it's part of the computation, which means we probably should deal with it. So that's what comes next. The partial derivative of z with respect to x is what? And then we negate that. So it's minus of minus 4 to positive 4. What is the partial derivative of our surface z with respect to y? Yeah, it's a negative 2, and then we have minus 2, so that's positive 2, and then 1, right? That's for free. So there we go. We got all the stuff. Let's put it in the soup, right? So
that formula for n is always gonna be true.
yes, because this is derived for plane.
Okay.
This one always be like if you had a parabola, you better not be using this as a normal vector, but it's a plane. So if you give an explicit definition plane, then we can use that number. In one sense, in the previous exam, if you kind of change the way you label some of the things, you actually come up with this. You've already come up with this derivation. You just use the different language in different contexts, but yeah. Okay, so now we can go back to finally answering what the original question was for crying out loud. So the line integral CF dot BR, this is what we're asked to evaluate. We can use Stokes' theorem, and we have the S curl. Okay, so do you remember on your notes, we computed what that curl was as a vector, and it was 1 minus 2y, 1 minus 2x, and 0. And then we're taking that as a dot product with what?
4, 2, 1.
Yeah, the normal, so 4, 2, 1. Let me think. Did I lie to you earlier about the Stokes theorem thing? I think I might have lied to you earlier.
Oh, we gotta
When you're doing Stokes, the construction of n is not. No, it is. It does need to be made into a unit. Hey, Dr. Harder, I think I can write a letter to Pearson. They have an editorial mistake. Yeah. Yeah. That's awkward. Let me think about that for a second to see if that actually affects the result though, because it might be technically possible.
What's the issue? The time?
Well, this is not a normal vector, but yet they're saying you can use that normal vector. Because it's fixed as normal to the plane. So how would that affect if you're just looking at them?
Cause I thought when we were doing whatever we were doing, normal, like, before this section, it didn't have to be.
It did, okay, yeah. This one doesn't need to be the unit normal, because remember the lecture we talked about where NDS being represented as the DS? And then when we did the derivation that the N construction is going to be the TU cross TV over TU cross TV. This in the theorem statement needs it to be unit normal because this magnitude is going to cancel when you did this curl, because there's going to be the component of TU cross TV that's going to be multiplied with this. So those are going to cancel this for the surface integral. So 421 is actually fine. So here, okay, we're not crazy. So we can use 421 here because we're converting this out of the arc length form, and we're going to use rectangular bounds instead of the surface parameterized. But that was a good question. I mean, I almost freaked out for a second. Yeah, that's how it is. So n is definitional unit normal by construction of the TU cross TV over the magnitude of TU cross TV. Yeah, when you convert it over to out of the parameter, then it's canceling with the magnitude, so.
All that was recorded, right?
Yes. Yeah. See, this is why I keep coming back to this, because I keep learning stuff about field theory. And this is my third time going through the curriculum, so. Good time. Oh, you know what? That's why I got myself confused. In my notes, I skipped a step, and so I've been imposing two different steps onto each other. This is R. Because we're referencing now in terms of the field. Yeah. Sorry about that. Okay, is that clear? So I duplicated this step, but then when I was duplicating this step, I was plugging in the next step.
Then we could use the and then we can use the whole long way to get the S.
You'd have to use the whole parameterize. You'd have to parameterize the point. We're doing just the explicit. Yeah, we're just using the normal. And use it with R. Okay. So as a means of recap, I made a mistake, and I put S here instead of R, which then made me think that this was supposed to be with respect to the other differential, and then I realized everything's wrong, because then that's not unit. Yeah. If with respect to R, we've made the substitution over into rectangular, so we can use 421. Okay, does everyone go with that? So if we show this, you're fine. Okay, and then we've got then, remember when we were talking about the region R, we have X's and Y. So the X was bounded between 0 and 2, if you refer to that region, and then the Y was bounded between 0 and, was it 4 minus 2x?
Yeah, minus 6.
4 minus 2x. Now we can take this dot product, right? So I'll do the algebra over here to the side so that we don't clutter up what we're doing. Algebra for the dot product. This, the X component with this, so we have 1 minus 2y times 4 plus 1 minus 2x times 2 plus 0 times 1. Okay, so that's obviously going to go away, so 0. And we have 4 minus 8y plus 4 minus 8x, which is just going to be 4 plus 4 is 8. And then, wait,
Did it 2.
no, that's a 2, sorry. Man, I need to sleep more. Okay.
4x.
2 times 1 is 2 minus 4, yeah. Well, okay. 6, and then minus 4x minus 8y. So this right here is this dot product, which is why we can now plug that. So we got 6 minus 4x minus 8y, and then the order of the differentials is what?
dy dx.
Okay. So here's what I'm going to do, because technically this is a unit 2 skill. I'm going to give you the reference points for your practice, that you can verify whether or not you're on the right track. So this, when you after doing the 0 to 4 minus 2x, so once you anti-differentiate this with respect to y, and you plug in the 4 minus 2x, then you should end up, once you simplify, with the outside integral 0 to 2. Minus 40 plus 36x minus 8x squared dx. So practice doing actually the integration, because you'll need to do it. I'm giving this to you so it's easy, more efficient for you to check your work. And then as another means, I mean, that's just calc 1 at that point. So here's what you should end up with. Negative 88.3. So here's what I'm going to ask you guys to do. Practice solving this problem, and more importantly, don't just see the individual pieces, as being random computations that you're doing. I need you to see that the only reason we can solve this problem is because Stokes theorem is allowing us to relate the line integral to this double integral, okay? So if you're going to use such a theorem, actually contextualize, oh, the reason why I'm practicing this curl is because, well, guess what? There's a curl in the integrand. So if I'm going to be substituting that in, maybe I should practice how to get that. And then what about the n? Well, if you have a plane, here's my normal vector for a plane, so you'll want to remember this for sure. And then the actual issue of plugging it in, recontextualizing out of the parameterized differential to r, and then you got rectangular coordinates with just dy and dx, it converts itself into a unit 2 problem. So you can do one integration problem instead of solving the 3 separate line integrals. Okay. Questions, concerns, comments? All right, finish strong, guys. We got one more. Friday, the last one.